Last class we started off with induction motor, and we saw the structure of an induction motor. It's very similar to what we have with the permanent magnet synchronous motor. As far as the stator is concerned, it's exactly the same. We have sinusoidally distributed windings, and when you pass sinusoidally time-varying currents, it's going to create a magnetic field in the air gap, which is spatially distributed. And as time goes on, the magnetic field due to the stator currents is going to start to rotate. Right? So we have already seen it for a permanent magnet synchronous motor. The same structure is retained for an induction motor as well. The replacement that we do for an induction motor is where we take out the rotor, which has magnets on them, and we instead put the squirrel cage structure, which is just a bunch of shorted copper bars in case of high power motors, and low power T points, typically aluminum bars, with some end rings which are shorting on both sides. Right? And there are no magnets on the rotor. And this has that you should look at this from a historical context of why they did this, because permanent magnet, all of these motors were invented around later part of 19th century, so around end of 1880s, 1890s. And the magnets that we know of, neodymium, those all come, samarium cobalt, all of those come after 1960s. Right? Even the Alnico ones, the cheap varieties, Alnico 5, that we have in our drive slab, which gave us like 0.35 Tesla magnetic field in the project. That one was invented, I think, around 1930 by some Japanese company. So this is much before that. So the magnets that were available back then didn't have the strength. And so what typically I had to do is on the rotor, instead of putting magnets, they were electromagnets. So you have to pass current into the field coil on the rotor to create the magnetic field, even for a synchronous motor. So it's not a permanent magnet synchronous motor, it's a field excited synchronous motor. And when we go to that, we again lose the benefits we got from moving from DC motor to AC motor. Right? Because to send current to the field coil on the rotor, you still need some kind of mechanical apparatus which can have mechanical isolation, still make electrical contact. We use what's called a commutator, instead of a commutator, a thing called slip ring, which is a full ring, and then a brush is just brush past it. So with that in mind, induction motor as a solution is an extremely brilliant solution because it doesn't require any kind of magnets on the rotor. It doesn't require any kind of field currents to be passed on to the rotor, and yet it creates a magnetic field which can then interact with the stator magnetic field to create torque. Right? So last class we looked at what the EMF profile of these rotor bars are going to be. As this magnetic field is varying in time, there's going to be an EMF induced across each of these rotor bars. And each of these rotor bars are extremely symmetric. They have the same resistance, same length, everything the same cross section. But we notice that the EMF induced across each of the bar has a sinusoidal distribution. Right? For this given orientation, which bar, let's say this alpha is 60 degree, which of these bars would have the highest EMF across it? You don't need to look at the formula, you don't need to remember the derivation, try to get an intuitive field. The reason we introduce the math of space vectors is to move beyond having to do the math, right? To give an intuitive field. So if the magnetic field is along this direction, the maximum of the magnetic field, which of these conductor coils would, which of these conductors would have the maximum EMF across it?
90 degrees.
90 degrees. Right? This one from here?
Yeah.
Okay. So let's go back and think about what would happen. So when you have your magnetic field maxima, which of these loops has the maximum amount of flux linking it? Is it this loop that I have drawn here? Let's call it loop 1. Or let's say there is a loop here, and let's call it loop 2. Does loop 2 have the maximum flux linkage across it, or loop 1 have the maximum flux linking? Loop 2, Thomas, thank you. So because if you look at this is the loop for which the B field is completely perpendicular. Right? If you look at loop 1, the B field is absolutely parallel. And what is our flux? It's going to be integral B dot ds. Right? So the B might be strong along this loop area, but the loop area is 0. So B dot ds would be 0 for this loop. So the flux is 0 for this loop, and the flux is maxima for this loop. If the flux is maxima for this loop, what will be the EMF across the loop? d phi by dt, right? Our EMF that's generated is going to be equal to the time rate of change of the flux. So if your flux is varying like a sine wave, your EMF is going to vary like a cosine wave, right? The differential of it. So when the flux is at 0, the EMF is going to be maxima. When the flux is at its maxima, the EMF is going to be 0. So this loop has the maximum flux, so that loop would have the lowest EMF. This loop has the lowest flux, and that loop would end up having the maximum EMF, right? So just by quickly looking at the diagram, you can figure out which one would have the highest, which one would have the lowest. But again, we derived this equation as well last class, and we assumed this value to be, let's say, some 100 volts. for some frequency, grid frequency omega e. And for now, we are only doing a fold count 2. I'll extend it a little bit later when we go to higher fold counts. Right? So when we have 100 volts, so this bar is going to be 100 volts. The bar behind it is going to be 100 times cos of 30 degrees. Right? And this one is going to be 100 times cos of 30. So you have 86.6 volts. This is going to be 50 volts, so on and so forth. So if you have 100, 86.6, 50, 0, negative 50, negative 86.6, negative 100, negative 86.6, negative 50, 0, 50, 86.6. Right, so we got a sinusoidal distribution in the voltage. Even though the conductors are exactly the same, every single rod is exactly the same, the voltage across them is sinusoidally distributed. Now, as time goes on, as this B field starts to rotate, this whole EMF profile is going to start to rotate along with it. Right? Yep.
That's like you have 0 to 0 across the loop that you said was the maximum, right? You have 0 volts and 0 volts across the loop that you said was supposed to be the maximum. Right?
Yep, the flux linking the loop is the maximum. So the flux is at its maximum, but the EMF is at 0. Right? Any questions? Okay. So as this BMS starts to rotate, the EMFs, the space vector, the rotor EMF also starts to rotate along with it. And we have achieved everything that the stator has achieved without doing anything special for the rotor with just a bunch of similar rotor bars. And because of this, we are going to have currents on the rotors, and we figured out how the current would come about. So whatever diagram I have there, I just put it in a planar form, just cut open it and look at it in a planar form. We have a bunch of voltages that have been developed across these bars. And to figure out the current through this bar, Ben gave the answer last time, Ben checked, where if you take the voltage that's available across each bar and divide by its resistance, that will end up being the current through that bar. Again, this was quite counterintuitive to come up with the answer, right? Because we have a whole bunch of sources and a whole bunch of resistors that are connecting into the network. But then we consider the case of a simple 2-source network. So we started off with just 2 voltage sources. And let's say this was 1 ohm resistor. We figured this current is going to be 100 ampere. And then we said, okay, come on, let's add some more voltage sources to this and analyze how it's going to vary. We have again 1 ohm, 50 volts here, 50 volts here, and then 1 ohm. So we wanted to figure out what the effects of the other bars would be on the current going through this rotor bar. So we applied our superposition theorem, and we broke it down into just 2 voltage sources, positive, negative, resistor, and then the other 2 voltage sources shorted, plus the current due to having the 50 volt voltage sources, and then the other 2 voltage sources shorted. And then the net current is just going to be the superposition sum of these two. Right? So we know already the current due to this voltage sources in this bar, we already calculated that will be 1 ampere. But now when we have the other voltage sources, the current due to this voltage source injecting into this bar is going to be the exact opposite of current due to this voltage source injecting into this bar. As long as we have symmetric bar distribution and the voltage across the bars on the polar dimensional opposite side, their diametrically opposite sides are exactly the same but opposite. The current due to the influence of those voltages on the other bars that are not their own is going to be cancelled out. Right? So effectively the current to every single bar is basically its own voltage divided by its own current. You raise any questions so far? Yep.
Sorry, I was just wondering with the diagram, why is alpha different than theta?
Theta is just a random arbitrary angle. Alpha is the angle at which the BMS is maximum.
Okay. But the peak EMF should be in the direction of alpha, right? Not.
Peak EMF will be up in the direction of alpha. That's where I think I've drawn it here for you. Right? Peak EMF 100 is at
Oh yeah.
exactly
that
where
makes
alpha
sense.
is.
Thank you.
Right? Yeah. So the theta is for this expression. For any arbitrary angle theta, what the EMF is going to be. Right. So we have the current flowing in the rotor bars, and once we have current in the rotor bars, it's going to try and establish its own magnetic field in the air gap. Before we jump to figuring out what the magnetic field in the air gap is going to be, we have to answer 3 questions. Let me see if I have space here. So what is the number of phases on the rotor? What are the number of poles on the rotor? And the direction of the rotor current space vector and the rotor EMF space vector. Let's start with the simple one. What will be the direction of the rotor's EMF space vector or rotor current space vector? Assuming that the BMS is along this angle, alpha equal to 60 degree, what will be the direction you associate for the stator current space, rotor current space vector? Or let's take one more step back. What will be the direction of the stator current space vector?
Same as B, right?
Same as BMS. So your stator current space vector, IS, is going to be along this direction. What is going to be the direction of your rotor current space vector? Or your rotor EMF space vector? Yes. There are only two possible options. Yep, James.
Is it the real axis?
Along the real axis. Why along the real axis?
Not imaginary, it's just that 0 degrees.
So the space vectors have nothing to do with the actual currents themselves. Right? Even in the case when we had stator current space vectors, all the three currents were real entities. Right? None of them have an imaginary component to it. What we are doing is putting it into a transformation that's basically saying that if the sum of these three currents are zero, which is the case for a three-wire system, then all of these points lie on a plane. And the space vector transformation is just a merely rotational transformation. Right? It's just a shorthand notation. The E part J theta is just a shorthand notation for doing the rotational transformation. Right? So that is what is introducing the complex entity to the space vector. It has nothing to do with the actual currents themselves. So even in this case, when I have the BMS space vector here, the B field due to each of the every single phases was the original real value function. Okay? But once we put it as a space vector transformation, you will get it to point along the direction where the net B field maxima would be. So going back to this question, it has nothing to do with whether your currents are real or, of course, there is no meaning to having a negative imaginary currents, but the space vector is not directly relating to the actual currents themselves in the sense of the actual phase values. Okay? Where would be the rotor current space vector?
Lagging by delta.
What was it?
Lagging by delta.
Lagging by delta. What is delta?
That was like the maximum, it's like the change from maximum of the B of the rotor, like the magnetic field of the rotor.
That's a good guess. So that was the case for a permanent magnet synchronous motor where we said the rotor was at some random arbitrary angle delta from the stator magnetic field. Right? But there, the delta was again our choice. We could control the delta to be at whatever angle, and we chose the delta to be at 90 degrees so that we can get the maximum torque for the minimum amount of current. There was a choice. But here we don't have the choice on the rotor. Right? The motor, the magnetic field on the rotor is not due to a magnet. It is automatically induced from the stator magnetic field. We have no control or say over what where the field is going to be. Right? So almost self-determined. Okay, so let's think about it. Which of these bars have the maximum EMF? This bar is along the 60 degrees, the one with the maximum EMF. Now can you tell me where the space vector would be?
Should it also be in the same direction, right?
Same direction. Thank you, Jonah. You fell for the trap. So E rotor is along the same direction. It is not. It will be 90 degrees behind, and we'll get to the reason why. So I assume Jonah gave the answer from the idea that space vectors point to the maxima direction. Right. So let's look at the case of the current space vector when we had so when we have our magnetic field space vector, it in reality is attributed to a physical entity, which is basically the peak of the magnetic field that's rotating in the area. But when we did the space vector transformation for currents and voltages, we made it very clear that it was purely a mathematical transformation which had no physical bearing to what's actually going on. Right? So let's look at the case where we have some current IA, some current IB, some current IC. When the current in the A phase at its maxima, so for the case where I have Im cos omega t minus 2 pi by 3, cos omega t minus 4 pi by 3, when omega t equal to 0, current in the A phase is going to be at its maxima. IA is going to be at its maxima value of Im. Right? And we know that the space vector for that case, IA space vector, will point along IA. So IS space vector would be 3 by 2 times Im e power j0, that theta would end up being 0 for this particular time instant. And as time goes on, the space vector starts to rotate. When B phase current becomes its maxima, the space vector will align around B phase. When C phase current becomes maxima, it will come from B phase to C phase. And in between, it will be all combinations going smoothly from one angle to the other. When the current in the A phase is maxima, think back to the sinusoidal distribution of the A phase winding. Where is the current density distribution the maxima? Is the current density distribution due to the A phase coil maxima along 0 degree or it's maxima at a different angle? Where is the conductor density distribution highest for A phase coil?
90 degrees?
90 degrees. So when we have our conductor distribution, if you remember, we had like one coil here, 3 coils here, and the maximum number of coils was at this point. Right? So if I do the Ni product is actually maxima here. And the Ni product is gradually reducing with the lowest value being along where the coil, the magnetic axis is actually present. So go back to our own drawing in this portion. So if I replace these conductors with those big sources and tiny sources, so instead of saying that this is 100 volt, let's say each of the resistance is 1 ohm, this is 100 amps, this is 86.6 amps, I can instead represent it as 10 coils carrying 1 ampere each and 10 amperes each, let's say, and then I can draw 8.6 coils carrying 10 amperes each, and then this would be 5 coils carrying 10 ampere each, and then here will be 0 coils carrying no current at all, right? So my current is maxima at this point 10 times, right? Same as the diagram that I have on the left there. When the current was maxima at 90 degree, Ni product was maxima, the current space vector was 90 degrees behind it, right? Same case here, my Ni product is maxima here, so my current space vector is going to be 90 degrees behind it. And since we are only considering resistive load for now, my EMF space vector is also going to be 90 degrees behind it. Everybody clear on this part? Right, so the EMF space vector and the current space vector does not have a physical implication to it, except we can make parallels to what we have in the circuit there. So given that it doesn't have physical implication, of course you're left to the choice that you can put them anywhere you want. Right? It has no physical meaning. You can, instead of putting e power j0, e power j2 pi by 3, e power j4 pi by 3, you could have started out with e power j pi by 6, e power j2 pi by 3 plus pi by 6, e power j4 pi by 3 plus pi by 6 is your rotational transformation. And you could have put your space vector wherever you want. But then when we look at how a transformer works, you'll see that this kind of alignment matches very nicely with what we have with transformers, where we have phasor notation. And we made an observation that phasors and space vectors end up being the same. If you were to freeze time at one particular instant and look at the space vector plot, it ends up being same as the phasor plot. Right? So when we look at the phasor plot, if we have this orientation, perfectly aligned with what we had before, and it also aligns with the physical interpretation that we have for current space vector, being that it's somewhat measuring the current density distribution and giving a surface direction to it, and the point where it's pointing is where we want the current space vector to be. Right? Everybody clear on this aspect? Yep.
Are the rotor current and EMF in phase because you're neglecting any inductive effects?
Yep. I'm just starting off with rotor resistance alone. We'll bring the inductor in just a little while. Okay. What will be the source of the inductance?
Loop area?
The loop area. Would it be part of? Let me not jump the gun. I'll get it. Okay. So before we proceed on analyzing what the magnetic field due to the current is going to be, is that rotor current going to set up a magnetic field in the air gap? In case of a permanent magnet synchronous motor, I could measure two distinct air gap magnetic fields. One due to the stator currents and one due to the rotor currents. Take a guess whether the rotor currents on the induction motor will have its own distinct magnetic field as well. Right? Everybody else? Okay. So let's to explain what's going to happen on the rotor side of a permanent induction motor. Let's go back to the analysis we started off on a transformer. So right now, whatever we have set up there is exactly a transformer. We have some magnetic field set up due to the primary coil, which is exactly what's happening here. I have some voltage, which is going to set up some current in this coil, and the current is going to set some flux in this coil, and the flux is going to link to the second coil. And using the idea that the flux on this side, this set of coil must be the same as flux linking this set of coil for an ideal transformer without any leakage inductance. We established this equation and we said that V1 by N1 must be equal to V2 by N2, which is the same as V2 equal to N2 N1 by V1. You have seen this again in different forms. Hannah mentioned the voltage balance equation that typically power electronics people try to use, but it all comes from the fundamental idea that things wound on the same core must have the same flux. So the idea is just the rate of change of flux must also be the same, and then the voltage would just be the rate of the turns. Okay. Now let's look at what's going to happen. So let's assume that this is no longer an ideal transformer, right? We're not going to worry about leakage just yet. If there is no load on the secondary, is there going to be current on the primary? If the secondary is open circuited like shown there, is there going to be a current? Right? What will be the current due to?
Magnetizing.
Magnetizing inductance. So even if you don't have a load on the other side, there is a magnetizing inductance element to it, which is going to cause some current to flow through it. Can you very quickly tell me what the formula for the magnetizing inductance would come out to be? Again, you don't have to memorize it. Just think of all the components that will be in an inductor. Just start throwing terms.
Permeability.
Perfect. Permeability, then
And turns.
in terms. So if you look at the flux, you're going to have the EMF equation, whatever we have. You have some flux going through some coil. The flux itself is going to have a factor of n times the current. So flux is going to be proportional to number of turns times the current. And then we introduce another term, flux linkage lambda, which is again n times the flux. Right? So you can think of the term that when you put the n, you should think whether there should be any some other higher power to the n. Right? The relationship we have between inductance and our flux linkage is lambda equal to Li. Right? And then the flux linkage itself comes from some flux itself comes from some current times the turn. So you end up with double counting the turns. So mu naught n squared. Any other terms?
Area and length.
Area and length, which comes in the numerator, which comes in the denominator.
Area on the numerator.
Perfect. Because it's a measure of flux. And then the length being the measure of the reluctance. And mu naught n square A divided by L. And since we have an iron core, it's going to be mu r. And this whole cross-sectional length, mean length of the core is going to be a LM, and assuming that the cross-section is uniform across all area. That was our aim there, right? So there's going to be some current as soon as you start to apply a voltage, even if there is no anything on the secondary, there's going to be current to establish this flux that's going on. And we figure out what that current is going to be. IM, the magnetizing current, is going to be the voltage that you have applied on the primary divided by 2 pi f times your inductance Lm. And when we did the demo for the permanent magnet synchronous motor using V by F control, the reason we kept the V by F ratio constant is because we wanted to control the flux in the core to be a constant. Right? So the flux itself in the core is going to be directly proportional to just the number of turns on the primary times the magnetizing current that's flowing through the coil. Right? So you wanted to keep this flux at the rated value, and to do that, we have to keep this V by F ratio constant because the rest of all the terms are constant in this diagram. So this is in case of a transformer. In case of an induction motor, the equivalent model, the only difference is that we have a tiny air gap in the core, right? Because the secondary side would be the rotor, the primary side would be the stator, and to provide some mechanical isolation so that the rotor can rotate, we introduce this air gap. How does this equation change when we introduce the air gap? As soon as we introduce an air gap, what can we say? We already know that the reluctance is only contributed due to the air gap. Assuming that the iron core has infinite permeability, this has droppers, no MMF at all of it is dropped here. For inductance is only determined by the air gap length, and the mu r goes away. It is just due to the air gap alone. Okay. So the mu r term is typically quite large, 4,000, 6,000-ish value. And the LG term compared to LM, the change in LM to LG is not as appreciable as the change from mu r to just mu r mu naught to just mu naught. Alright, so typically when you introduce this air gap, the inductance would start to go down. And that is quite a bit of a problem because when the inductance goes down, you would need appreciably larger amount of current to establish the same amount of flux in the core. Right? So in case of an induction motor, in case of a transformer, typically the current that you would require for magnetizing at rated values would be typically less than about 1% for a line transformer, less than 1% of what the load current is going to be, rated load current. In an induction motor, that value is typically between 10 to 30%. How do we reduce that current? What can we do in an induction motor to minimize the current, the magnetizing current? Adjusting for the LG. Right? If we can reduce this LG as small as possible, then we can increase this LM so that the current can be lesser to create the same amount of flux that we need. Right? So in an induction motor, we can reduce this because there are no magnets stuck on the stator. Right? So this length can be quite small. In fact, for quite a high power motor, it can be as tiny as like 0.1 millimeter. Right? Okay, so coming back to a transformer, let's now introduce some load on the side. And let's start giving some values. Let's say this is 10 volts sinusoidally varying at some frequency. And what is going to be my voltage V2? Oh, I need to give you the numbers. Let's say this is turns of 1:10. What's going to be the secondary voltage? 100. Just a step of transformer. 100 volts. Let's say the resistance here is 100 ohms. Then the current on the secondary is going to be equal to 1 ampere. What is going to be the current on the primary?
10 amps.
What was it?
10 amps.
10 ampere? 10 ampere here or here in a diagram?
Coming from the voltage source.
Coming from here?
Or no, you're right. It would be 10 amps going into the transformer alone.
10 amps here alone. There will be some current IM depending on what the inductance is, and the total current here is going to be IM plus your 10 ampere. Why is it 10 ampere? What was the logic? Power balance. Perfect. So you have your V1 I1 must be equal to your V2 I2. So we have, what was the voltage that we have? 100 volts, 1 ampere, 10 volts must be 10 ampere. That's one way of doing it. Not as satisfactory. Any other answers?
Cancel the flux.
Cancelling of flux. Perfect. Why should the flux cancel?
It's enclosed.
It's what?
It's an enclosed surface, complete surface.
That would have been the case previously too, right? This coil established a flux fine, but this coil didn't try to cancel that initially established flux. Why is it trying to cancel the flux now? Because we connected to an infinite voltage source. The minute we put a voltage source there, the magnetizing current was determined as the voltage source divided by 2 pi f times Lm. Once the magnetizing current is determined, the flux in the core is determined. N1 times the magnetizing current. Right? We have put a voltage source because of which the magnetizing current was determined. And the minute the magnetizing current was determined, we have determined the flux that's going into the core. Now, if the flux were to change here, that would then mean that the IM has to change. That would then mean it would try and change the voltage source that's there, which is not possible. So whatever current this drew and whatever flux it created, the only option is for the primary coil to cancel out the flux right away, right? Instantaneously. So what we have is the flux created due to the second current is going to be proportional to N2 times I2, and this must be instantaneously cancelled out by an equivalent flux coming from the primary coil, which is proportional to N1 times I1. So N2 I2 will be equal to N1 I1. And then you have your I1 is equal to N2 divided by N1 times I2. Hopefully, if you plug in the values, that should all match up. This was 10 by 1 times 1 ampere. You end up with 10 ampere, which matches up for whatever we did before. Right? So, whatever current goes on in the secondary, that is not changing the flux in the code. Right? Because whatever current this draws, it's going to try and set up a current. Instantaneously, the current is going to be cancelled out by whatever we have on the primary. There's going to be an equivalent current drawn on the primary that will cancel it out. Now, going back to my earlier question, will there be a flux in the air gap of an induction motor due to the current on the rotor? How many of you say no? Just one. How many of you say yes? How many of you are ambivalent? So, coming back to this case, we have the exact same setup here. We have our stator here, we have our rotor here. There is a current going in the rotor. It tries to establish a flux on the rotor in the air gap, but that flux is instantaneously cancelled out by an equivalent current drawn from the stator. The same thing would happen for an induction motor. Right? The moment this current comes about on the rotor, it will try to establish its own B field in the air gap. But the problem is the stator is connected to a voltage source. So the flux in the air gap cannot change, no matter what you try and do. So the only option is for the current to be drawn on the stator to compensate and cancel out whatever the flux was being created due to the rotor currents. Right? So it will be instantaneous if we are ignoring all the leakage inductances for now. Right? So it will be instantaneously gone. So the only flux in the air gap for an induction motor will just be the stator current induced flux alone, with no contribution coming from the rotor currents. Do we have any questions? A very critical point, because in a permanent magnet synchronous motor it differs quite a bit, because there are two distinct B fields which are independent and which operates at the same time simultaneously. In this case, there is just one set of B field that's going to be in the air gap for this ideal case. Now let's start introducing some couple of other parameters. We have some resistance in the winding of this coil. So let's model that with a resistor, right, on the primary side. Now all the flux that's here, all of it is not going to go and link to the secondary coil. Some of it is going to leak away. If the iron core is infinite permeability, then nothing will leak away. But once the iron core is not infinite, once we assume a practical iron core, or even if you don't assume a practical iron core, even if you have mu r as infinite, you introduce the air gap here. Right? So this air gap path compared to this air gap path, this would have a little bit higher reluctance compared to this tiny path, but it's still a path that's available to the flux to flow through. So some of this flux will leak out and it won't link to the secondary coil. So that you can model it as a leakage inductance. LN. Okay. Why do I put it on the left side and not on the right side? So in all the equivalent circuit transformer diagrams, I've always seen it on the left side, but not on the right side.
Because it occurs before the core.
It doesn't occur before the core, it occurs at every single point on the winding. Right? We are using this bulk model for inductances, but it's actually the wire going across the core. Every single point equivalently drops some kind of inductance, some kind of resistance. It's like a distributed pi model kind of. Right? So it is not like one single block I have, and then all of the inductance are lost there, and then we have remaining. So why do we put it on the left and not the right? So the idea is whatever current flows here, the total current flowing into the transformer, right, both due to the secondary current as well as due to the magnetizing current, is going to establish a flux, and some component of that net flux is what is flowing out. Right? If you try to put it here, then this component of the current that established the flux to begin with is not captured at all in your drop in the inductance that we have. So we put it on the left, and the same reason for the resistance. Why did we put the resistance on here and not here? Because the current that created the magnetic field in the first place, that is also going to get dropped across the coil as it flows through the coil. Right? If you put the resistance here, it will only drop the current due to the secondary current being reflected on the primary, but not due to the current of the magnetizing itself, which again is going to go through some wire and drop the value across there. So in our equivalent circuit, these two terms come on the left, and then we have a magnetizing inductance. We do the same thing for the secondary side as well. Not all of the flux on this side is going to link back to the primary. Some of it is going to leak away. Okay, we moderate some leakage reactance on the secondary, and the coil itself is going to have some resistance in addition to whatever resistance we have outside. R out, this is external world, but the coil itself has some resistance, R2. Okay, so this is going to be a equivalent model. Everybody clear so far? So let's go back to our, let's look at the phasor diagram for this. So we have some voltage V1. Where shall we draw the current phasor? Let's say the IM phasor. Okay, let's start off with a simple case. Let's go back to this semi-ideal model where there is some magnetizing inductance, but there is no leakage, there is no resistance. Let's start with a very simple case. Where will the IM current phasor be? The direction of the IM current phasor?
Is it leading by 90 degrees?
Is it leading or lagging?
Lagging.
Is it leading or lagging? Are you going to flip again?
I think it's leading
Why is it leading?
because it's J omega L, and the phase is 90 degrees ahead. Yeah.
So is the current leading or the voltage leading?
The current is leading.
Current is leading the voltage. Alright, so you have your expression V equal to J omega L times I. Like, what does J do? J does a rotation along 90 degree. So if you have the current at some x-axis, the voltage will be 90 degree forward.
Oh, okay.
So the voltage is the one that's leading and the current is the one that's lagging. Okay? So you have your IM current phasor, which itself was equal to V1 divided by omega E, which was 2 pi F, times your magnetizing inductance Lm. Okay. So let me introduce this convention called dot terminology. There are different ways of thinking about it. One way that's quite useful is if a current passes into this loop, starting at the dot terminal and creates a flux, some phi, along, let's say, this direction, then the current going into this loop must create a flux along the same direction as well. That is what the dot convention is. If you have a bunch of coils, and if you pass current into one of the coil along the dot terminal, and it creates a flux going in this clockwise direction, every other coil, if you inject current into the dot terminal, it will create the same clockwise going flux. That's the terminology. You can bring this top from the top to the bottom, the dot, by just rewinding it in such a way that instead of coming out and going like this, if I flip the winding and reverse it around, you can just flip the dot convention, dot to the bottom side. Right? There's no complexity to it. So if the voltage is positive here and negative here, the voltage will be positive here, negative here, if the dot is on the top for both cases. If the dot was flipped around, the positive would be here, negative would be here. There's nothing particular about the transformer having positive voltage on the top or the bottom. Okay. So let's look at where the secondary side voltage phasor is going to be. Where would you put the secondary side phasor, voltage phasor? There are two possible answers. I would take either answer as okay.
Same direction as B1.
Same direction as V1, right? So let me put it here and I'll explain in a second why that I'm doing it. Can you tell me why it would have been in the same direction? What equation would you use to prove that it's the same direction?
Like the power balance equation.
Power balance equation. We don't even need to go to the power balance, right? Which is V2 was N2 divided by N1 times V1. We could use that, or another way of thinking about it is this flux. This current created some flux phi in the core, and the time rate of change of that flux is what is creating the voltage on the secondary. And so it's same logic that Ganesh said this should be 90 degree lagging. You have V equal to L di by dt. Right? So the current is the voltage is the differential of the current. Then the current was 90 degree behind the voltage. Now in this case, we have our voltage, which is the differential of the flux phi. Okay? So same logic that you can use to say that your V2 would have been in this direction. So we choose a dot convention in such a way that we flip the voltage phasor, and in a second it will become evident why we do that. So take this for granted for now. Once I draw the reflected state rotor currents on the primary side, it will become quite clear. If this is the phasor for the rotor side voltage, what will be the rotor side phasor current? Again, let's assume these are all ideal. What will be the direction of the rotor current phasor? Very trivial question. Vertical? Why vertical? What is the relationship between the rotor voltage, the secondary side voltage V2 and the secondary side current I2? It's just the resistive load there, right? So it has to be along the same direction. I2 phasor, that is just V2 divided by your R load that we have there. So we have a current on the secondary side. And now this current is going to cause an equivalent current to go on the primary side so that the flux doesn't change in the core. This is what we saw already. So that we're going to call as the reflected rotor current. And can somebody tell me what this value would be? In the example that we did, this was 1 ampere. What did this come out to be? So I2 prime is basically this current. What was the current?
10 amps.
10 ampere. Which is N2 divided by N1 times I1. End up being 10 ampere. Again, I've drawn it as if it appears as if they are the same length. That won't be the case. This would have to be drawn much longer. But in the homework, if I give like a set of normally large transfer range, you can just draw the same length, just put the magnitude along there to indicate their different amplitude lengths. So the reason we put this in the other direction is because here the current is leaving the dot terminal, I2. In this case, current is entering the dot terminal, right? And we cannot put the I2 on the other side because that would mean there is some generative action going on the transformer. So what is going to be the power flowing into the transformer? It's going to be V1 times I2 prime. That's the power going into the transformer. If I had made I2 prime on the other side, then it would be meaning that the transformer is giving power to the primary power supply, which is not what's actually going on in the circuit. So to keep this portion of the diagram faithful, we choose a dot convention on this side so that the current is leaving out of the dot terminal. Again, I could have chosen such that the current, let's say, going into this terminal as the actual value, and then the diagram would have drawn like this, the V2 would have been drawn like this. But we make a deliberate choice of putting the dot terminal here so that the reflected current is along the voltage and the secondary side current is 180-degree opposite to it. Right? So this part of the diagram is completely optional. You can choose however you want to do on the other side, confuse everybody out. But it is nothing wrong physically speaking. But this portion definitely has to be in phase if you are putting an resistive load on the other side, because power is going from the primary side and being taken out on the secondary side. Everybody clear to this part? Here's the diagram of a transformer. Let's say I replace this resistor load with an inductive resistive load. Some L, some R. Will the IM change? V1 definitely is not going to change. So before we jump there, how do I figure out the total current here? I1 total current coming from the source. What do I do? The phasor diagram, how do I get there?
Just add IM to the reflected I2.
Just add the IM to the reflected I2. This is going to be your I1 total. Right, so going forward, when I call I1, I'm going to be using the terminology. I1 is going to effectively be the I1 total. Right, this is what we are going to call as I1. This we are going to call as reflected secondary side current as I2 prime. So whenever you have that prime character put on top, that means that something going on the secondary that's being reflected as an equivalent current on the primary. Right? Okay, so now let's say I start increasing the inductance on the load side. Is IM going to change? Is IM affected by what's going on the load? Absolutely not, because it was just the primary voltage divided by its own inductance. That's still going to stay there. The EMF induced on the secondary is also not affected. Just direct relationship. What is going to happen to the current on the secondary side?
Will start to lag the voltage.
Will start to lag the voltage. By what factor?
And inverse of the impedance of L over R.
Okay, so let's call this alpha. So this is going to start to lag. That means the reflected current is also going to start to lag. And the reflected current relationship is right there. It's just a scaling factor. So this is going to be your reflected current, and your net current is going to be again the sum of these two. I1. Previously we were calling it as I1 total. Equal to the magnetizing current plus the current flowing on the reflected current flowing on the rotor. Right. So this is where the problem again is. If we have what is the disadvantage of having a very large IM? Why do we want to minimize the IM as much as possible? What is the objective of reducing the area of an induction motor? What is the problem? Why not just have a high IM current?
Core would saturate eventually.
Or will saturate it eventually? No, you can choose a, if your inductance is quite small and you use a high IM current, the flux would still be quite low. Right? You are using a very high IM current because your inductance was quite large. So if your inductance, magnetizing inductance is reducing, then you would increase your magnetizing current to compensate for the fact that you want the flux linkage to be the same. Right? So the flux linkage is still the same in both cases. So the core is not saturating before, it's not going to saturate now. So what is the reason we still want to keep the IM very, very low?
Losses?
Losses, perfect. Another answer? Losses is the primary concern when you have a drive connected induction motor, because you still need higher current to establish the same flux, which is then going to lead to higher I square R losses. But let's say induction motor, typically the advantage is you can directly line connect the induction motor. For a grid connected induction motor, what's the problem?
Power factor?
Power factor. So as this vector keeps becoming larger and larger, IM, the net current moves farther and farther from your voltage, V1. Right? And the angle between the voltage and the net current is your power factor phi. So as the power factor starts to increase further and further, you're consuming more and more reactive power, which has its own problem, and the grid operator would put a penalty on you if you start to take quite a bit of amount of reactive power. Right? So for every kVAR that you consume, the grid operator is going to put a huge penalty on you. So you would have to have some kind of compensation mechanism, put some capacitors or something, so that the reactive power can come back that has its own expenses. Okay? Any questions so far? So let's come back to our induction motor. So let's put all the pieces of the puzzle together. So on the induction motor we have, we'll start off with our this is the same convention the book is using. So the currents, EMS current, phase vectors along this direction. So this is the stator current that is intrinsically, so basically this current flowing into our equivalent model that we have for our stator magnetizing inductance. And the BMS phase vector is going to be along the same direction. Where is the rotor voltage phase vector going to be? We already saw this. So let me ask you the other question. Where is the rotor current phase vector going to be? Anybody?
90 degrees behind, right?
9 degrees behind. Right there, the drawing that we did there. So the induced EMF on the rotor is going to be 90 degrees behind from the magnetic field that caused the voltage in the first place. Where is the rotor current space vector going to be? What will be the direction of the rotor current space vector? Let's start out with the simple case. If the rotor was purely resistive, where will the rotor current space vector be? What was it?
Same direction.
Same direction. And if there was some inductive load,
90 degrees. Or
right? A combination of inductive resistor,
alpha. probably.
some alpha. Inverse omega L sugar R. The R is very obvious where it's coming from. It's basically the rotor bars having some resistance. Where is this inductance coming from for the rotor? What is the source of that inductance? Go back to whatever we have the diagram on the transformer. The reason we drew the transformer is exactly for this case. Where was the source of the inductance in the transformer? Let's say I didn't put an RL load, would there have been an inductive source on the transformer?
LM.
LM we already modeled it on the primary side. Leakage, perfect. So going back to a transformer model, what we have there, in case of an induction motor, how this changes is basically, instead of a load, we have some resistance due to the coil itself, and then some leakage inductance due to the coil again, right? Because the flux is leaking on the rotor side without leaking the stator, and then this part is just shorted out. Right? That's what our end rings are effectively doing for us, shorting the whole system together. So this L is going to be a rotor leakage inductance, this is going to be a rotor resistance. And the origin for this is basically because when you have your rotor bars, and then you have a bunch of stator windings, this is going to create some flux. Only the flux that links back to the stator coil can be seen by the stator coil and cancelled out, exactly as what was happening here. Only the flux that went and linked back, to this was cancelled out by an equivalent current being drawn from the other side. But if the flux leaks and does not link back to the primary coil, there is no way for the primary coil to know that the flux has changed within this one tiny section. And so this is not going to try and compensate for whatever that additional current was required to maintain the leakage flux component of it. Same thing happens here as well. So whatever the tiny leakage component is, that is not going to link back to the primary, and the primary doesn't know about it, and it's not going to compensate for it either. Right? So we are going to have some leakage flux, BL on the rotor, and the B on the rotor due to magnetizing part, that is the one that will be cancelled out. So this flux will not exist, this component of the flux will exist in the area, right? Because it is not going to be cancelled out. So this component is basically modeled by the tiny inductance that we have, and the leakage inductance of our rotor. Okay. If this is our BMS, where is our EMF on the stator going to be? So going back to our transformer diagram, there will be this voltage. That will be our EMF. Where will that be? If your BMS space vector is along this direction, where is your stator back EMF space vector going to be? What is the source of the stator back EMF? Let's go back to the case of permanent magnet synchronous motor again. In case of permanent magnet synchronous motor, what was the source of the back EMF? There are two contributions due to back EMF. And you didn't calculate both those contributions in the homework, last question. What were the two things that were contributing to the back EMF in the permanent magnet synchronous motor? Anybody?
The rotor spinning, one of them,
Rotor spinning, one of them, and the other one?
the inductance of the stator electromagnet.
Inductance of the stator electromagnet. Where was the EMF due to the inductance of the stator electromagnet? Due to LM. Let's say again for the permanent magnet synchronous motor, the BMS was here. Or let's go due to the, let's say this is the rotor magnetic field BR. Where was the magnet EMF induced due to the rotor magnetic field? in case of a permanent magnet synchronous motor? 90 degree, so d5 by dt. They have the EMS this side. So this is going to be a rotor current. This is going to be the stator current that's establishing the magnetic field. Is that all the stator current is going to be? Is this the only current that's being drawn from the stator power supply? For the induction motor that we have? Or is there any other current?
I2 prime,
What?
I2 prime.
I2 prime. In our case, rotor current prime. Because again, going back to this diagram, you had some magnetizing current IM. This IM is same as our IMS space vector in the diagram. Right? And then we had some I2 current here. The reflected current of that was I2 prime. In our case, we have rotor current IR here. And then reflected rotor current on the secondary primary side. And some of these two currents is the net current being drawn from your power supply. So some of this, like this, is going to be your net primary current drawn from your power supply. How will I figure out the terminal voltage on the primary side, on the stator side? What else do we need?
Back EMF from the rotor spinning.
Back EMF from the rotor spinning. That is already attributed.
Then
There is no rotor magnetic field at all, right? Because whatever rotor magnetic field was is instantaneously cancelled out by the stator magnetic field. In case of a permanent magnet synchronous motor, the currents in the stator established a magnetic field BMS. That in turn created an EMF that was the drop across the LM. And then there was a magnetic field due to BR, which in turn created an EMF, which was the magnetic field ER, which was induced on the stator winding, which we put as a parallel coil. In this case, there is only one magnetic field in the air gap, which is BMS. Due to rotor magnetic field, whatever it was trying to set up, except for the leakage component, everything else is cancelled by an equivalent current drawn on the second primary side. Right? So this is the only voltage source. Okay, what else do we need? Or do we go from EMS to the terminal voltage? You go back and look at the transformer diagram. Answer is all there. So what I have is basically EM. I'm asking how do I get V1? If there is no RS, LLS, then it's exactly one of the same space vectors. If I have resistive inductive drop on the stator side as well, right, due to the stator winding resistance, and then the stator's own leakage inductance, LLS, because the same diagram that I drew there, I have some rotor bar, some flux only links the rotor bar and not all of it links back to the stator. Same thing happens with the stator-rotor relationship. Some flux of the stator winding only links to itself, not linking all the way back to the rotor winding. Right? So that's going to have its own leakage drop that we are going to be modeling. And that's going to drop some voltage. So due to the resistance, it will be along this direction. So whatever this direction is, this is going to be IS space vector times the stator resistance. And then some drop due to the inductance. This is going to be 90 degrees from this. So omega times LLS times your stator current space vector. And the net sum of all three is going to be your stator voltage space vector. Okay. You guys any questions? So the homework for this week is basically trying to solve this problem. Do this a bunch of times. This is definitely going to be on the exam. So take your time and try to figure these space vectors out. Next week, we still have a little bit of time, don't leave. But next week we'll derive a whole bunch of torque equation and all of this just from this space vector diagram. without having to go back, like for an permanent magnet synchronous motor, we looked at the magnetic field in the air gap and tried to figure out the torque by doing integrals all over the air gap field. But none of those complications are no longer necessary because we clearly showed when we did for permanent magnet synchronous motor, but just by looking at space vector, you can figure out all of those relationships. Right? All linear operations get translated when you do space vector transformation. Non-linear operations do not transfer though, right? Okay, so we have addressed one question, the direction of I and D. So here again, when we address this, I said when we look at the phasor diagram, we'll again make the case that it has to be behind by 90 degrees. I think that is clear because if you look at the phasor diagram there, when you have your current going in the perpendicular direction, IM, the EMF induced on the secondary side was 90 degrees behind it from the phasor diagram. Right? Nothing to do with space vector notation. When we come back to a space vector notation, we said that we'll assume the rotor coils to have this kind of profile, even though they are individual bars, so that they reflect what's happening on the stator, and we'll draw a space vector along this direction. The choice of drawing the space vector on the rotor was quite arbitrary, but using this arbitrary notation, it would match well with whatever we have in our phasor diagram there. Right? So this was arbitrary choice. You could have put the space vector anywhere, but using this notation where we are going to model whatever is on the stator on the rotor, it would match perfectly with whatever we have on the phasor diagram. Just to keep that relationship still going, we are going to retain the same idea. So let's do both of these. If I have a 4-pole induction motor, what will be the number of poles on the rotor? And the other part of the question is, if I had a 3-phase induction motor, what will be the number of phases on the rotor? Answering the question about phase is a little bit tricky, but let's start with the question about poles. If I had a 4-pole stator, what will be the number of poles on the rotor? Take a guess.
4.
4. Why 4?
Because there's just 4 regions that are going to be formed by the 4 poles of the stator.
Fantastic. So while I draw that, in the meantime, somebody can come with another answer. What was the reason? The reason the number of poles on the stator had to be equal to number of poles on the rotor for a permanent magnet synchronous motor. What was the reason we gave? What would happen if the poles are different? If I had a 4-pole stator on a permanent magnet synchronous motor and a 6-pole rotor, what would happen?
No torque.
Why don't talk?
They're orthogonal.
They are orthogonal. Okay. So we went back to our concept of Fourier. You can model your stator magnetic field as, let's use cos. Some cos of P by 2 times, in our case that's 2 times theta. Let's say it's a 4-pole motor. So the stator magnetic field looks like this. The rotor magnetic field is going to look like some other constant. Cos of, and if you had a 6-pole there, it will be cos of 3 theta. A torque is basically the inner product of these two in some sense. Right? So B is BR, some constants coming here, and integrate over the full volume of the air gap. And we have already seen that these two products, these functions are orthogonal functions. The only way the product, the integral of this product would be non-zero is that these two coefficients are exactly the same. Right? So same as when we did the frequency transforming, we had sine 3x, and let's say we had sine 3x. This integral is non-zero. But if you had any other number, doesn't matter what that number is, over a single full cycle, this number is always going to be 0. Right? So by the same logic, we know that induction motors do operate and produce a torque. So just based on that reason, the rotor poles, however it develops, must be exactly same as the stator poles if there is going to be torque produced in the system. Otherwise, from our Fourier analysis, we know that there is going to be no torque produced at all. So let's visualize and see what's going on. Jack gave the perfect answer because when you had a 4-pole on the stator, what would have happened? You would have had some BMS magnetic field peaking here and then going to 0 within 45 degrees and then reversing direction, having the negative peak here, and then you have reversing direction again. Right, so you have for this due to the stator, the stator profile. Now, if you look at the rotor rods, so this along the north would have created the maximum voltage. In our case, there was 100 volts. And the one along the south would have created negative 100 volts. In between, it would have transitioned to 0. This would have been 0 again. This would have become positive 100 volts. This would have been 0. This would have become negative 100 volts. This would have been 0. Right? And then this would create a current such that this is 100 ampere, 0 ampere, negative 100 ampere, 0, negative 100, negative 100, 0, negative 100, 0. And that if you look at the magnetic field that's created by the rotor, that would end up again having 4 peaks. With one peak being along this direction, the other peak, negative peak being along this direction, positive peak along this direction, and then negative peak along this direction. So whatever you have the pole distribution, B field distribution on the stator, same B field distribution profile would be created on the rotor as well due to the currents that are induced on the rotor. Right? So looking at that profile, the number of poles on the rotor is exactly same as the number of poles on the stator. And there is nothing you need to do about it. There's nothing you can do about it either. Because all of these rods are exactly one and the same. It is just that the matter of induction that whatever B profile is in the stator due to the stator currents in the air gap, that is what is inducing a voltage on the rotor. And that voltage would vary in the same way the B field is varying. Which in turn means the current would vary the same way the voltage is varying. Which in turn means the magnetic field that it tries to establish, which it cannot because the stator would cancel it out, would again be in the same profile as what the currents are. So if the stator had 4 poles, the air gap field due to the stator current would have had 4 peaks, 2 positive peaks, 2 negative peaks, and then the EMF that is induced on the rotor would have had 4 peaks. The current due to the EMF on the rotor would have had 4 peaks, and the B field it tries to establish would also have 4 peaks, right? Okay, so let's get to the tougher question. How many phases are on the rotor? Let's say the stator is a 3-phase motor. How many phases are on the rotor?
Is it just one?
It is 1. Any other answers? It's a very good answer.
What does it mean to have a phase on the rotor?
So if I were to, I'll address that question in just a second. I'll get all the answers and then come to the question. Answer. Any other answers? So before I answer yours, once again, can I have, if I have one, let's say I had one phase on the stator, what was the magnetic field profile? Was the magnetic field able to rotate on the stator if I had a one phase system? But in our case, the rotor magnetic field is rotating. Our rotor space vector, the EMF space vector, which was along this direction, when the BMS space vector was along here, as time went on, as BMS rotated, R and IR also would have rotated along with it. Right? So if I'm trying to model the rotor as an equivalent circuit, and if I model it as a single phase system, I cannot create rotating fields on the rotor. But clearly the fields on the rotor are rotating by the virtue of it coming from the stator, but it's still rotating. Right? So it cannot be modeled as a one phase network. Is that clear, Jonah? Okay. What else can it be then? From purely a modeling perspective, if I want to model this rotating field mathematically, how many phases should I have to represent it as? Just to make the rotating field come about.
2.
2. Is that the only answer? What else?
Need more than 2.
Any more than 2? So there is no requirement that the rotor, there is no concept of phase on the rotor side. Right? Exactly going back to the question that Ben had asked, what does it mean by phases on the rotor? There is nothing meant by phase on the rotor. There are no terminals coming out, nothing is happening there. But if you want to model what's going on mathematically on the rotor, you need to model it as some polyphase circuit, either 2, 3, 4, 5, whatever you want to choose. What would be the optimal choice? You can model it however you want. You can model it as a 2-phase circuit, you can model it as a 3-phase circuit, you can model however you want. But if you're modeling it, what would be the best choice to have? Yep.
Would be the number of rods.
Number of rods? Why the number of rods?
I don't know, because you had drawn it, like the voltage sources is the number of rods.
Okay. Not stop. It's okay. Maybe I'll do that case as well. Number of rods. Is there any other options?
3.
Why 3?
You can leverage maybe some of the concepts that are used in MAC motors.
Which is?
Is the constant power beneficial?
The concept of constant power is true for any polyphase system. Even in a two-phase system, the power is a constant. Because we have sine omega t times sine of omega t plus some 5 plus sine omega t minus pi by 2 times sine of omega t minus pi by 2 plus 5, the power would still end up being a straight line.
Would it just be for simplification of calculations when you're in reference to the stator?
Perfect. Which simplification in particular?
Um,
When we use the circuit for a permanent magnet synchronous motor, what was the circuit called? The equivalent circuit. There was a added term prefix to it. So
steady state?
steady state and
Per phase.
per phase. So when we have a three-phase network, right, at steady state, you can just look at the currents of one particular phase and tell everything about the other two phases. So you can take a three-phase network and break it down into a single one-phase network at steady state alone. So if you want to do the same reduction of this three-phase system to a one-phase system, it will be good to have the rotor be modeled as a three-phase system as well. So let's look at what's going on. So this whole diagram that I did is just a one-phase transformer. In our case, we have three phases. So we have some resistance, some leakage inductance of A phase, and some voltage source on the A phase. And then we have some magnetizing inductance. Rotor leakage inductance, rotor resistance. And then similarly, we have other two transformers as well, all of them owned on the same code. For the other two phases, VB and then VC. And these coils coupled with one another too on the stator side, which we already saw, was the origin of the negative half Lm in our inductance. So we have LSB, LSC, RC, RV. Hopefully all of these values are the same. They needn't. LSB, some LM. Clearly we cannot use a one-phase coil on the secondary side, right? Because if we use a one-phase coil, then the concept of rotating fields cannot be created. So we need to put at least two coils here on the rotor, two-phase coils. So this is absolutely fine. So mathematically you can create this model. So here the voltages would have been cos omega t, let's say. This would be omega t minus 2 pi by 3. This would be omega t minus 4 pi by 3 cos of. On this, you can model it in such a way that this comes out to be some cos of omega t. Again, we haven't considered the case where the rotor has yet started rotating. It's all stationary plus some phase phi. And this can be cos omega t minus pi by 2 plus phi. Mathematically, you can absolutely model this and there will be nothing wrong. You can derive all the equations that we are going to be doing next on Friday using this simple model. But the one thing we cannot do is at steady state. We cannot say I'll just analyze this circuit alone and then figure out what the other phase currents are going to be. Because this one you can couple it to this does not couple to anything else. There is no way of symmetrically splitting this. So the way we can symmetrically split this as one single steady state equivalent circuit is we put a third coil and say this is omega t plus some phi minus 2 pi by 3. And this is cos omega t plus phi minus 4 pi by 3. And in steady state, I can just analyze this network alone, ignore these two, and whatever currents I get here, if I want to figure out what the currents for the B phase is, it's just going to be 2 pi by 3 phase shifted. The C phase current is going to be just 4 pi by 3 phase shifted. Alright, so just to make our equivalent steady state circuit easy to analyze, we are going to model the rotor as well as a three-phase system. Right? Or same number of phases on the stator is same as the number of the phases on the rotor. This is only a modeling requirement, not a mathematical requirement. It's not a requirement, physical requirement. But the number of poles being the same, that's a definite physical requirement. Alright, because the pattern that's established in the diagram. The number of phases, that is totally up to you. If you take it in this form, it makes your life much, much simpler. So with that, let's end today's class on Friday. You know, the derivation for the torque and complete the rest of it.